Hello. In this video, what I'm going to do is go through inverse relationships or inverse functions, and then different types of inverse relations. So we'll look at linear relationships, quadratic, exponential, and then their inverses and what that actually means for something to be an inverse. So we'll go through a couple just table graph equation problems. That's basically it. I'm going to start off by definition, what an inverse actually is. Inverse relations are those where your x and y coordinates are reversed. So all you do is flip-flop the x and y's. And what it does, it produces a graph that is really a reflection over the line y equals x. So the line y equals x is really y equals 1x plus 0. Like 0 is your y-intercept, your slope of 1. So just to give you an idea, that would be something that looks like this. And what we're going to do is see that I'm going to plot a line, and then that's a really bad line. I'm going to plot a line, or plot a bunch of points that make a line, and then when I reverse their coordinates, you're going to notice that it just turns into a reflection over this blue line I just drew. So I'm going to first plot these points, so 3, negative 4, negative 2, negative 1, and then negative 7, positive 2. And I'm going to cheat and use my little line tool because that first attempt was so bad. Alright, so that was a lot better. There we go. So what I've got then is just 3 points. They make a line. We can probably even determine the equation of that line, but I'm going to skip that for later. So what we're going to do is flip-flop these coordinates. So my inverse coordinates then, and you're not changing signs or anything, but I would have negative 4, 3, negative 1, negative 2, and then 2, negative 7. And what we'll see is if I plot these, I'll see my reflection. So negative 4, 3 is going to the left 4 and up 3, negative 1, negative 2, and then I've got positive 2, negative 7, so over 2 and down 7. And if I connect the dots on those, and I'll do that with a dashed line, so I'm going to connect the dots on those, which again, wow, poor lines today. It's not my day. Alright, there we go. So connecting those dots, you can see again, I've got this reflection. The solid black line versus the dashed black line are reflected over this line of y equals x. So if I were essentially just to fold this graph kind of over from the top left corner to the bottom right corner, you would see a total reflection on the graph. So what an inverse really does, well, we've heard the word inverse before. Solving equations use inverse operations. So you're really just looking at things that are opposites of each other. So what we're going to look at is how to actually find those equations. Before we do that, let's take a look at things that are nonlinear. So I'm going to take an exponential relationship and then show you the inverse of an exponential relationship, which is a logarithmic function. And we're going to do this the same way. All we're going to do is flip the points. So I'm going to just do that first, actually. I'm going to take these x values, which now become my y values, and then take my previous y values from the exponential relationship, which now become my x values for the logarithmic one. And all I'm going to do is plot these points. So I'll do the original function, which is exponential in red, so negative 2, and then I'm going to go up a quarter, which is like here, negative 1.5, 0, 1, 1, 2, and then 2, 4. So I've got a nice exponential growth equation, something like this. And then if I plot the coordinates that are in blue, so I'm going to start with the 4, 2, and just work backwards. 2, 1, 1, 0, 1 and 0.5, and then go over a quarter and down 2. And if I draw these, we can see that I'm going to start getting closer and closer to that y-axis. Wow, this is really not my day. Alright, so I've got these two curves, and again, all that we did was plot my original coordinates, and that's the red curve, represents an exponential growth. And then if I just flip-flop the x and y values, which they call transposing, so if I flip those x and y coordinates, I end up with this blue logarithmic curve. At the end of the day, it still relates back to the first problem. We have a reflection over the line y equals x. And that demonstrates that these two functions, or these two graphs, are inverses of each other. So we're going to get a little bit more into what it actually means for something to be an inverse. And here's just some brief steps into how you would actually find an inverse function. So we'll start off in function notation of f of x, which we're going to switch to y, and then transpose, so again, flipping our x and y values, and then really just isolating your y. So again, the word inverse comes in. We're using inverse operations to get this new function. So I'm going to give it a go on this. This way we can actually see then what the graph of the original function looks like, and then what the graph of our new function is going to look like. So I'm going to start off just graphing this function. So f of x equals 2x minus 6 is a line, it's a linear relationship with a y-intercept of 0, negative 6. And then my slope would be up 2 and over 1. So if I go up 2 and over 1, and do that a couple times, get a nice straight line, which again, my line's going to suck, so I'm just going to connect the dots here. Alright, there we go. So here's my original function, which I'm just going to draw in black, solid black line. So that represents our original graph. And again, just to show you, I can just pick another point, 1, negative 4. And if I wanted to get my inverse graph, right off the bat, I can do it just by flip-flopping the x and y values on these 2 points. I'm going to hold off on that for a sec, and we're going to jump to the equation part of this. So I'm going to find my inverse equation by following those 4 steps. So I'm going to switch my f of x to y, and bring the rest of this down. And then it said to transpose x and y. So basically interchange x and y. So I have x equals 2y minus 6. And then it's just a matter of isolating the y. The goal is to now get the y by itself. So I'm going to do so by adding 6 to both sides first. And then to isolate y, again, I can just divide by 2. That's the inverse operation. So the word inverse comes in again. And I'm just going to rewrite this as y equals, because the y is now isolated, and I have x over 2, which I can rewrite as 1/2 x, and then I have a positive 6 over 2, which is really a positive 3. So the last step is to rewrite my inverse equation as a function. So I say f with this little negative 1, which represents f inverse of x, and that is 1/2 x plus 3. So now I'm going to graph this line. So this line has a slope of 1/2 and a y-intercept of 3. So I'm going to start up 3 and then go up 1 over 2. And here I can go down 1 to the left 2. And then I'm going to switch here and get this. Oh, now we're on a dashed line. Cool. I've got a dashed line, and I'm just going to play connect the dots through those points. My goodness. All right, there we go. Adjust that a little bit. All right. And again, at the end of the day, what we need to see is that if I found this correctly, I should be seeing a reflection over the line y equals x. And we do see that. If I wanted to know at what point these 2 equations would be equal, that would just be solving a system of equations where I would just set the 2 equations equal to each other. But what we'll notice then is if I were to flip-flop or transpose these coordinates, I would have negative 6, 0, and then negative 4, 1. And what we'll notice is if I go to negative 6, 0, that is on my inverse line. If I go to negative 4, 1, that is also on my inverse line. So it brings me to the next point then. I'm actually going to go back a slide for this. How to verify if 2 functions are inverse of each other is if their composition is x. So what that really means is I need f of f inverse of x to just equal x. Okay, so what that means is if I were to pick some value, and let's just say I took x, and I added 2 to it, and then I multiplied it by 4, and then I divided that value by 6, and then I got some new value of y. If I wanted to work backwards, I would just undo my order of operations. So if I went from this y value, I could multiply by the 6, I could divide by the 4, I could subtract by the 2, and I would be right back to where I started. So doing some operations and then taking the inverse operations is essentially just going to undo each other, and you'll get right back to where you started. So what we're going to do is just take our inverse function, which is the 1/2 x plus 3, and I'm going to substitute that into my original function. So my f of f inverse of x is going to end up being, and it was 2x minus 6 was our original function. So our original function, the 2x minus 6, in for that x value, I'm going to substitute my 1/2 x plus 3. And all that I'm going to do is simplify this. So distribute the 2. So 2 times the half x, so 2 halves is 1x. I have 2 times the positive 3, which is positive 6. And then I'm going to bring down the minus 6. And what we'll notice is if I simplify this one more step, the 6's cancel, and I'm left with x, which is what we wanted. We wanted the composition just to come out to x. So that proves then that these two functions were inverses of each other. And I'm just going to take one more approach at this, or one more look at a problem that's not a linear relationship. So I've got a quadratic equation in this case, and I've got one that's in vertex form. So what I'm going to do is just complete this table of values for this first function, and I know that my vertex uses these two values, so the hk values in this case, I would have -3, -2, and I'm going to throw that in the middle of my table of values, and then just pick the numbers that are around it, so -2, -1, and use -4, -5, and if I complete the table of values around this just by substituting these values in, I'm going to get a -1, and then I would get a +2. So again, I'm going to first just plot these points, starting with my -3, -2, and then I can just plot my remaining points, which is going to give me something like this. So here's my parabola, and I'm going to try my best to draw this graph. Again, horrible, not my day, doesn't matter, it's a parabola, we get that. So this is my original graph, f of x. And right away, I'm going to plot my inverse function by just flipping my coordinates. So my inverse table, I would take my 2, -1, -2, -1, +2, which were the y coordinates. Those now become x's, and then these x's are now going to become my y's. So -5, -4, -3, -2, -1, and then I'm going to plot these. So I'm going to go over to -2, -3, which is here. I've got -1, -4, -1, -2, and then 2, -5, which is down here, and then I've also got 2 with a -1. And I'm going to dash this, and then label this as my f inverse of x. And again, this idea that, hey, here's my line y equals x, and if I were to fold this corner on top of the bottom right corner, I would have the perfect reflection. So in order to figure out what the inverse equation is, same as the linear equation, all that I'm going to do is follow those same steps. I'm going to take this f of x and replace it with the letter y. I'm going to flip my x and y, or transpose them. And then we're just going to be careful and do some inverse operations here. So the first thing I'm going to do is bring this 2 to the left-hand side by adding it. That's going to give me x plus 2 equals y plus 3 squared. And then I can square root both sides. So before I subtract the 3, I need to square root both sides of this. So I'm going to throw a plus minus in front of this left side, x plus 2, and that is equal to y plus 3. So now the squared part is gone. And then at the very end, I can swing this 3 to the left by subtracting it. So I have -3 plus minus the square root of x plus 2, and that's y. So then at the very end of this, I can replace that y with f inverse of x, and that is -3 plus minus the square root of x plus 2. So if I were to graph the -3 plus the radical x plus 2, that would account for the top part of this sideways looking parabola. And if I typed in a calculator -3 minus the radical x plus 2, that would produce the bottom part of this graph. So if you were to use your graphing calculator to verify this, you would have to put this in as two separate equations for the plus minus. What I'm going to do then is verify this using composition. So the same thing that we had done with the linear relationships, I'm going to take my original function. So in order to do f of f inverse of x, take the original function, which had something squared minus 2. Oh yeah, something plus 3, I should say. Something plus 3 squared minus 2. So I took an x value, added 3, squared it, and then subtracted 2. So in for that x value, I need to substitute this entire new function. So that's going to go here. I'll just write it really small. And then we'll just start simplifying. So the first thing I'm going to notice that cancels out are the negative 3 and the positive 3. So now I've got this plus minus square root of x plus 2, and then the minus 2. And the square and the square root are going to be the next things that cancel out here. And that's going to take the little plus minus away with it. And I'll be left with x plus 2, and then bring down my minus 2. The 2's are going to simplify next and cancel out, and I'm left with x. And that's what we wanted in order to verify this, which proves that our functions were inverses of each other.